Welcome back, everybody. Well, we are definitely ready to talk about some integrals this time. We're going to talk about definite integrals. So let me remind you of the sort of big idea behind integration. So we've seen some examples in our previous videos where something was changing, the velocity or the height of a graph. So we couldn't use old algebra formulas like distance is rate times time, or the area is always the height of a rectangle times its width. So what we did is we broke the interval where the independent variable, usually x if we're talking about a graph, or it was t if we were talking about velocity because our variable was time. We break that interval up into little pieces. And then we would pretend that what was changing wasn't on each of those pieces. So, for example, when we were doing velocity, we pretended that the velocity was constant over each little time interval. Now, of course, it would be a different constant on each interval, but throughout that little interval, we would pretend that the velocity was constant. Or when we were finding area, you might have a graph whose height is changing, right? So it's not a rectangle with a fixed height and a fixed width. But what we could do was break the area into little rectangles by pretending that, by cutting the x interval where the function is defined into lots of little pieces and pretending that the height of the graph was constant for each of those little pieces. That makes lots of little rectangles. We could find the area of each of those rectangles and then add them up, right? So when you do that, you get a Riemann sum. And we've talked a little bit about summation notation and how this big sigma with an f and of t and a delta t, or an f of x and a delta x, is what we would get when we start adding up all those little pieces. And something like that's called a Riemann sum. Now, if we use more and more pieces, then we would get the right answer. In other words, we would get the total distance that some object has traveled given its velocity. Or we would get the area underneath some curve by breaking up things into smaller and smaller little rectangles. And we said that what you get when you take the limit of a Riemann sum as your delta t goes to 0, right? Well, that's a definite integral. So let's be very precise about how we define this so that we're completely clear on how this is going to work. So if we have a function f and it's defined on some interval, say ab, then we would say that f is integrable on that interval ab. In other words, it has an integral and it exists. If this limit exists, so okay, what's this limit? Well, let's look at it carefully. So first, the limit is delta x goes to 0. So that's the width of each of these subintervals. And we're assuming we've broken this up into equal subintervals. Then we take the sum from k equals 1 to n of f of xk, and our book writes a star there. I'll explain what I mean when I put a star there. Then the width of each of these intervals, delta x of k. Okay, so here's the thing. The xk star is meant to represent the idea that, as we saw in the previous videos, we could find the height of those rectangles by using the left endpoints or using the right endpoints. Or when we're doing velocity, we might measure our velocity at the beginning of one of these subintervals or at the end. And it didn't really matter either way. If our function was nice and continuous, it all kind of washes out in the limit. So assuming that everything works the way it's supposed to, it shouldn't really matter whether we use left endpoints or right endpoints or midpoints or any point in between. So that's the reason for the star. The xk star means just pick some point inside that interval. Maybe the left endpoint, maybe the right endpoint, maybe somewhere in between, and use that to evaluate my function. And assume that my function is constant with that value throughout the interval. Now multiply that by the width of the interval, add all those pieces up, and take the limit as our pieces get smaller and smaller and smaller. If that limit exists, then we say that our function is integrable, and this limit is what we're going to call a definite integral. Okay? And now notice that I write the integral symbol. It looks an awful lot like our symbol we use for an indefinite integral. It's a little squiggly S sign. But now we have upper and lower limits, right? An a and a b, because this function was defined on some interval from a to b. So we imagine this is like starting at a and going to b. If we're talking about an area, that makes sense, right? We're finding the area above the interval ab on the x-axis, the area above that and underneath the curve. Or if f were some sort of velocity, then this would be the distance the particle traveled between time equals a and time equals b. Okay, so let's state now on the slide, so it's all nice and official, that the area under a curve really is going to be a definite integral. If you have a nice continuous function, and the function is bigger than or equal to 0, that's important. If our function dipped below the axis, then we start getting negative values of f, and we don't want area to ever be negative. So suppose that our function is always going to be above the x-axis, then the area, above the x-axis and underneath the curve, given by the graph, right, that will be equal to this definite integral from a to b f of x dx. Okay, so this is the kind of thing that, again, I'm a mathematician, so I'm sort of contractually obligated to say this next little bit. But it is interesting when you compare this to what we know about differentiability. So what this theorem says is that if you have a function which is continuous on AB, then it's integrable on AB. Right? So in other words, if you have a continuous function, then the integral will exist. Now, think about that for a second. That's almost exactly the opposite of the way the story worked when we talked about differentiation. So if you had a function that had a derivative, right, if you have a derivative, then your function had to be continuous. But there are plenty of examples of continuous functions that didn't have a derivative. Absolute value of x doesn't have a derivative at 0. So just because you can find a derivative, right, meant you were already continuous. But just because you were continuous didn't mean you had to have a derivative. Here, though, as soon as you're continuous, the integral does exist. Now, that's an interesting thing. That means that the sort of integration is somehow easier, right? You can have an uglier function. For example, you can't take the derivative of absolute value of x at 0, but you can definitely integrate it anywhere around 0. So, I'll give you 20 seconds of historical background here. This sort of thing was known and understood, soon after Isaac Newton was figuring out how calculus works, and Newton and Leibniz were discovering it, fighting over who should get the credit for it. This would be, late 1600s and thereabouts. So this question of, well, exactly when is a function integrable, right? How bad could it be? For example, could you have a function which is not continuous and still be integrable? Does that make sense? And the answer turns out to be yes. Suppose you had a function which is continuous, and then there was like a break, and then it was continuous again. Well, then you could just find the area, say, by doing it in two different pieces. So having a couple of 3 or 4 or 5 or some finite number of breaks in your graph is still fine. You can still find the area under it. What if you have infinitely many breaks? Right? How bad can it get? That's a very interesting question. And it's not until the early 1900s that all gets sort of satisfactorily figured out. And that's the topic of a class that you might run across, say when you first start studying your PhD in mathematics. Okay, so again, because I'm a mathematician, I sort of feel like I must tell you these things. And more often, more with this than with other things, this actually turns out to be really important. So what happens if you were to switch the limits around? In other words, suppose you have a function which is integrable on some interval ab. You could write the integral from a to b. Right? That's normally how we would think about it. We'd start at a and find the area up until we get to b. But could we write the integral the other way around? In other words, could we go from b to a? Right? You can, though, it's perfectly good sense. What happens, though, is you get minus what you started. And this kind of makes sense if you think about this, where f is a velocity. Right? If you traveled, from A to B, then traveling from B to A is sort of going backwards. So obviously it sort of makes sense if there's a minus sign in there. Well, what about if you integrate just from A to A, right? You have a function which is defined at A, right? And you just integrate from A to A. Well, the answer there should obviously just be 0. The reason, of course, is if you think about this in terms of area, this makes sense, right? What would the area under a curve be if you started A and ended A? Well, there's no width. The width has got to be 0. So it doesn't matter what the height is. The width is 0, so the area should be 0. Well, okay, what are some other properties here? Well, if you had two functions, which both are integrable on AB, then we'll call this linearity. We've seen this thing before in several guises, as we talked about limits, whenever you take a function, right, and multiply it by a constant, call it r, and then add or subtract, say, either way you want to do it, another constant times g, you can break that up in kind of the obvious way. So we saw this already with antiderivatives. If you take f and it's multiplied by a constant, you can move the constant and stick it outside the integral. If you are adding two functions together, you can integrate one, then write down a plus sign, then integrate the other one. Or if you're subtracting, it works the same way. So just like this works with limits, because this is a limit, right? A definite integral is exactly just a limit as your delta x went to 0. You also have this relationship about what happens if you have two functions and one's bigger than the other one. Now again, if you think about this in terms of either height of a curve, to find the area, or velocity, and we're trying to find the distance, if, say, g is bigger than or equal to f, then when you do the integrals, well, the integral of g will be bigger than or equal to the integral of f. Because if g is bigger, of course, right, its graph is sitting on top of f. So the area underneath the g should be more, right, because the g graph is smaller and it has a smaller area under it. Or if you think of f as a velocity, when you say, how far did you go, right? Well, if the f function is slower, right, if that velocity is smaller, then you don't go as far as you would if the velocity were larger. That was the g function. One other thing you can say is, suppose that you have three numbers, a, and then b, and then it's broken by some c in the middle. Then integrating from a to b is exactly the same as integrating from a up to this breakpoint c in the middle. Then starting again at c and going to b. Again, this makes a lot of sense when you think about this in terms of, say, velocity. If f were a velocity function, right, and then we integrate that velocity from a to b, that'll tell us the distance we traveled between time a and time b. Well, what the right-hand side of this rule says is if I went from time a up to time c and found the distance I traveled then I start up again at time c and keep going until I've reached time b, then of course I find a new distance I've traveled and add those two distances together. It's obviously got to be the same as the distance I traveled just when I figured from A to B. Area, of course, works the same way. It makes perfectly good sense. This is really important because it lets us do things like break an interval up into several pieces. This will be important with things like, well, I mentioned the absolute value function a few minutes ago. The absolute value function is weird. The graph is that sort of V shape, right? It's really defined to be negative x when x is less than or equal to 0, and just x when x is bigger than or equal to 0. So if you wanted to integrate an absolute value, right, the easiest way to deal with that is to treat it as two different functions which stick together at 0. So if you wanted to integrate an absolute value function from, say, -5 to 5, the easiest way to do that would be to integrate it from -5 to 0, because then the absolute value function has one formula, right? And then add to it what you get when you integrate from 0 up to +5. Okay, well, here's another example of the kind of questions that you can ask and that you can see in the homework where we use these sort of rules, especially this subdivision rule. So suppose I tell you that you have a function, and when you integrate from -2 to 1, you get 3. When you integrate from -2 to 7, you get -5. Can you use those two things together to figure out what happens from 1 to 7? And if you think about it, it's not too hard. What we can do is, well, write down this equation, right? When you take the integral from -2, smallest number, all the way up to 7, the biggest number in these various limits, that's the same as going from -2 up to 1, and then going from 1 up to 7. And that's sort of obvious, and again, it uses that idea of breaking up the interval into pieces. I've got a break point there at 1, where I've broken this area. But of the 3 integrals I've written down, the problem told me the value of 2 of them. It told me that the integral from -2 to 1 was equal to 3, and the integral on the left-hand side of the equal sign from -2 to 7 is negative 5. So there we go, right? I know 2 of the 3 numbers, so just take that extra 3 to the other side. And the integral that I'm asked about, the integral from 1 to 7, that's just negative 8. Okay, so we can play this game over and over. So I'll do an example with lots of different parts. So here we're going to give you 2 facts. The integral from negative 1 to 1 of f of x is 0. And the integral from 0 to 1 of f of x, same function, is 5. And it's got to be the same function, right, to be able to put these together this way. So I want to ask 4 different things, so A, B, C, and D. Let's do A first, right? Can we figure out the integral from negative 1 to 0? Okay. Well, yeah, we use the same idea of playing with the breakpoints. So start with the smallest endpoint that we know, negative 1, right? And the biggest endpoint we know, which is 1. That would be the same as breaking it at 0, going from negative 1 to 0, then 0 to 1. And, as luck would have it, right, 2 of those integrals are things that we know. Right? We know the integral from negative 1 to 1 because the problem told us that was 0. I know the integral from 0 to 1 because the problem told us that was 5. So then the integral that's left from negative 1 to 0, that's the one we're asking for. We just solve, take the 5 to the other side. We can do something similar with B, right? So they ask for the integral from 0 to 1, and then subtract the integral from negative 1 to 0. Well, we know the integral from 0 to 1 is 5. They told us that in the problem. And just a second ago, I have erased the screen then, but just a second ago we worked out that the integral from negative 1 to 0 was negative 5. So 5 minus negative 5 would be 10. For part C, they're asking us to find the integral from negative 1 to 1 of 3 times f of x. Well, remember, 3 times f of x, I could pull that 3 outside the integral. Right? And so that just multiplies 3 times the value of the integral from negative 1 to 1 of just regular f of x dx, which we know to be 0 from what they told us in the problem. And of course, 3 times 0 is 0. But if I try that again from, say, 0 to 1, again, I pull the 3 outside the integral and use the fact that the integral from 0 to 1 of f of x dx is 5. We know that from the problem. Then 3 times 5 gives us now 15. Okay, well, I've used the words, definite integral all throughout this video. And previously, we talked about indefinite integrals. So an obvious question might be, what's the difference between a definite integral and an indefinite integral? And are they connected at all? Well, the question of how they're connected, we'll wait till a future video. That's a very, very, very interesting story. But at the very least, let me remind you of how this goes. The difference between the two, at least for now, we can say that a definite integral is really a number, right? It's an area or a distance, depending on how you want to interpret what the function f is. But a definite integral evaluates to give you a number. An indefinite integral, so it doesn't have those endpoints, just the integral sign, that's an antiderivative plus c, right? It's an entire family of functions.